Welcome to video 3 in the Materials and Inventories module. And in this video, we're going to cover a couple of what I'll refer to as utility concepts that we'll use a little bit later on. The first one is routing from a transfer node. The second one is the constraint element. And the third concept is using data tables for bill of materials data. And for this module, or for this video, I don't have any more slides. We're just going to start with a base model. And as before, I'm going to go through the details of this base model, and then you should stop the video and make sure that you can replicate the model. It's a really straightforward model. You can see here that we have a source and it creates entities, and we send those to the transfer node. We then use the transfer node to select one of the three servers. So if you look, we're using that select from list feature that we've seen before, and we're just using the associated station overload. And so what should happen here is entities go to this node and it selects the server that's most likely to have remaining capacity, and the servers again have capacity zero input buffer. So the decision of routing is going to be made here at the transfer node. And then when they leave this, when they leave the transfer node, they go to the sink. Okay, so we also note here that the server, we're using a task sequence, and we're using materials and bill of materials here. And so if we to see how that's working, go to our data definitions, and you can see that I have 5 materials defined. I guess that's 6 materials. I have part A and part B, which are, we're going to think of those as assembled parts. And so they both have a bill of materials. Part A requires 1 unit of raw 1 and 2 units of raw 2. Similarly, part B requires 1 unit of raw 3 and 2 units of raw 4. So part A has raw materials 1 and 2. Part B has raw materials 3 and 4. And so we're just assuming these are materials, so we're not using inventories for this. We're just consuming the and producing. And so if you go look at our servers, the 3 servers have the same set of task sequences. First thing I'm going to do is I'm going to consume the bill of materials. So we're using the bill of materials here to consume from the corresponding material inventories, and I'm using the reference in a data table. So we have a data table named parts, and the reference is .mname. So go back to data, and we have a data table where mname is material element property. So this is these are our 2 finished goods, part A and part B, and then we're going to randomly generate rows. So I have a mix here column. And so in the server process, we have that reference. I'm going to show how we get the reference here in just a second, but we consume the raw materials. We then go through a simple processing step, and then we produce the finished goods. So in the case of part A, we're going to consume 1 unit of raw 1 and 2 units of raw 2 here in step 10. Then we're going to process, and then we're going to produce 1 unit of part A. Part B, it's the same thing, except that we're going to consume raw 3 and raw 4. And so again, a very simple process. Our source, we just generate using we have a table row reference that we set when we create the entity. And so we just use a random row. That's where the mix column comes in. And that's the base model. I also have a materials plot here, status plot that has 6 rows. And so what we are tracking here are the quantity in stock of all of our materials. So part A, part B, raw 1, 2, 3, and 4. And so if we run the model, we can see that we're just creating parts randomly, and they're being routed using that the logic of overload, minimum overload. So that's going to send it to the server that's most likely to be available. And when a part gets to the server, we're consuming the raw material, so that you can see for raw 1 and 2 we're consuming, and raw 3 and 4 we're consuming, and then we're producing our part A and part B. When we get to 0 inventory here, though, for raw 1, raw 2, raw 3, and raw 4, now we're blocking. So we're blocking trying to consume the inventory that doesn't exist. And you can see that, let me just pause the model here, everything is backed up. Since I have a connector here, everything is backed up in this output node. oops, I wanted to drag that actually. And so you can see that we have, our mix of part A and part B and part A and part B that are being blocked from being transferred by the material constraint. So this part A is being blocked by the material constraint. This one and this one are all blocked by the material constraint. And the fact that these are all 3 part A doesn't really mean anything. It's just random chance here. Okay, so hopefully that base model makes sense. And as I said, you should stop the video and make sure, or create this base model that we're going to use for the rest of the video. Okay, so I'm going to go back in and change a couple of things. First thing I'm going to do is I'm going to go back into my definitions, and I'm going to take the 2 components for part A, which would be raw 1 and raw 2, and I'm going to make them assume infinite availability. So that we just put a 1 there because we want it always to be true, and then we're going to do the same thing for raw 2. And so now both components for A have infinite availability. And so now when we run our model, we're going to see that the inventory for A can now potentially go negative. The inventory, for raw 1 and raw 2, the components. So let's just let those components go down. So I guess raw 1 is the light blue one, and raw 2 is the, red one? So we're producing, and we can see that. When they get to 0, then they're going to go negative. So they go negative here, right there. We just had it go negative. So now all 4 raw materials are we've taken them all or used them all up, but because raw 1 and raw 2 are infinite availability, we can continue to produce those and let those inventories go negative. But now if you look at the situation that we have, all of our part Bs are blocking. So all 3 servers have part Bs that are waiting, and now we have this inventory, we have this queue of parts of both type A and B waiting here at the transfer node, or actually they're waiting in the output buffer, but they're being held by the transfer node because we don't have capacity on any one of the servers. Okay, and so you can see this if I go back in. Let me just go back in really quickly and change the mix so that I don't get any part Bs. All right, so let's just set that to part A. So just make that mix 0. And now when we run, then the model's never going to stop. The inventory is going to continue to go negative and negative and negative and more negative. So we're tracking that back order inventory, but it's not going to block the model. And so we'll see it get down to 0 here in just a second. There we go. Now they're going to negative, but we're not going to stop because the inventory is assumed negative. So the problem here is that if we have these both arriving like we had before, the question is this really what we want? Because we have part A's that are being blocked, but they're being blocked not because of the inventory condition, they're being blocked by the capacity condition. And so the fact that we have all of the part B's consuming all of the server resources when their corresponding materials are unavailable is forcing the part A's to also wait, even though their material constraint is not appropriate here because we have that inventory policy, the inventory infinite availability set to true. So what we really need to have happen, what we'd like to have happen, is have the inventory constraint checked here at the transfer node. Right? Have the inventory constraint checked here so that we can not route entities to the server unless the corresponding resources, the corresponding materials are available. And to do that, we need to use a constraint logic element. So I'm going to go back to my definitions, elements, and what I want is right here, constraint logic. So let's just put one and rename it BOM constraint. And we can see that we have a repeat group here for the constraints, and we're going to add a constraint. And the constraints are several types. We have material availability, we have resource availability, and we have a condition. For this one, we're only interested in resource availability. So we have resource availability, and now our consumption type is bill of materials, and the material name is specified in our data table. So we have parts, M name. And so now what we're saying is that we have created a constraint element that says, I want to require the bill of materials for the corresponding part to be available. And so the last thing we need to do here is then go attach that to our transfer node. I'm going to click our transfer node there that we saw earlier, and we had that select from list. And right here we have this other routing out options. So we're just going to select that, and then we're going to add our route constraint logic. So just click right there, and we want to add our route constraint logic. And because we've already defined this as a bill of materials constraint, that's all we need to do. And so now when we run the model, let me go back and verify that I have this set up right. So we have part A, part B, and then for raw 1, we assume infinite availability. In raw 2, infinite availability. Raw 3, no infinite availability. In raw 4. So exactly what we saw before. But now what's going to happen is the material availability, instead of being checked once an entity gets to the server by that task, by task number 10, it's going to be checked here at the transfer node. And so when we run, now what we're going to see is when I run out of raw materials 3 and 4, the part B's are all going to get blocked, but the part A's are going to be allowed to pass through the transfer node because their corresponding raw materials have infinite availability. So where before we saw that we eventually the system spot because we had all part B's in the server, we shouldn't see that here. We should not see any part B's once their corresponding materials are at 0. And so we see that here. There are no material 3 or 4 available, but we have infinite availability on raw material 1 and 2. So all of the part A's are allowed to go through, and all we see here in this queue are part B's. So all the part B's will never proceed unless we replenish the corresponding inventory, but we're not blocking any of the part A's. And so you can see in effect what we've done is we've moved the enforcement of the bill of materials constraint, whereas ordinarily it was right here. So when we have these tasks, you're saying, okay, we have a material requirement here to consume, and so it was blocking when they got to the server. We've moved that constraint back to the transfer node by using this route constraint element. And so that's something that we will see all the time when we do scheduling type models. This example of the constraint logic element, we only use material availability, but recall we also had resource requirements and general conditions. So for example, I could also hold entities here if I need, say, a secondary resource. So let's think about having a server where you have a secondary resource to do a setup or something like that, and you don't want to use the capacity on the server until that secondary resource is also available. So we could move those kind of logic constraint, or the constraint material, or the constraint logic, I should say, back to the transfer node, right? So again, if you think about having that secondary resource here, you would actually go to the server and then you would block there, waiting for that secondary resource, exactly what we saw before we did the material constraint. So I'm not going to demonstrate that here, but that's something you should also have a look at. Something else that comes up or that you might be asking is, so why are we using this transfer node? Because I could do the exact same thing here, because the output for the source object is also a transfer node. So just select that, it's right here. And so if I if I did the destination type and select from list, and we have all of that same logic available here. And so we could, let me just get that back to normal. We could do the exact same thing from the output of the source. Well, the reason we use this transfer node is it makes the model a little bit more flexible. So if you think about this whole part here that I have, the transfer node and the 3 servers, as one workstation. So I have these parallel workstations, and I'm using the overload logic to go to the one that's going to be available first, right? Think about if I wanted to use that as part of a sequence, right? So I want to specify that the parts go to this workstation, okay? And so I could, in the sequence, include the transfer node rather than the individual server nodes, because I don't know which server I'm going to go to. So in the logic, in the sequence for the entity, I would specify the transfer node. Similarly, suppose that I have another similar workstation here, so that entities that come out of this block then go to another block with servers in parallel. Then I want to have, if I have a transfer node that would be right here, I have a single decision point. as opposed to if I have them directly from these transfer nodes, I have multiple decision points. So what I'm trying to do by incorporating the transfer node is add the flexibility so that I can use a part sequence or an entity sequence and also have the single decision point, even if I'm coming to that transfer node from multiple locations. And one last thing I want to mention about using the transfer node is once we set this up, recall that when we use this select from list option and we want to use the overload function that we've done here before, all of these buffer capacities are 0. And so as we want, that makes the decision point back here. There's no dispatching decision to be made in the server. So when I look at the server ranking rule and dynamic selection rules, they don't mean anything because there's no buffer. So there's no list of waiting entities that need to be processed. But all of that can also be done at the transfer node. So if I go back and choose the transfer node and then look at these other routing out options, we see those two options right here. So we have the ranking rule, and we also have the dynamic selection rule. So that same logic that you can use for the individual servers, we can also use at the transfer node. And so when we say incorporate a standard dispatching rule, then we have the constraint logic element, which is enforcing the material constraint. Then we have the dispatching logic and ranking rule that order the entities that we're going to look at. Then we have the destination selection that's being made by the destination type. So you have the constraint, then you set the sequence that you're going to look at the entities that are waiting at the transfer node. And then when you come to an entity, you have the destination logic that's saying, okay, where is it going to go? And so we'll see all of that in more detail when we get to the ISA 95 template and the models that are based on that. The last thing I'm going to demonstrate in this video is moving the bill of materials information to a data table. So you can see here that we have our bill of materials defined with respect to the material element. So I'm going to go in and reset. Well, actually, let's copy this model. Let's duplicate the model and work with the duplicate. And so we'll rename it BOM table so that we can keep our original version. So let's just go there. And then I'm going to go to my definitions, and now I'll get rid of the bill of materials, right? And so to get rid of the bill of materials, delete both of those, and then delete both of these. So now they're no longer explicitly defined with respect to the material element. And I'm going to go in data, and I'm going to create a new data table. So create a new data table, and we're going to call this BOMS for bill of material, plural. And I'm going to link that back to our part. So we had already defined parts as a column key. So the first thing I'm going to add is a foreign key property, and we will call this mname, and then set the table key value to the parts mname. And then we'll define our component material. So I'm going to go to my element reference property. We need a material. We'll call this component material. And then define the quantity. So component material and then quantity, QTY, not ATY. Try that one more time, QTY. And then I can define my bill of materials here. So I'm going to do part A, and part A required 1 unit of raw material A and 2 units of raw material 2. And part B required 1 unit of raw material 3 and 2 units of raw material 4. Oops, not 22, 4, 2, sorry about that. And so then if I go back to my parts and I use the detail view, you can now see that I have bill of material for part A is 1 unit of raw 1, 1 unit of raw 2. B is 1 unit of raw 3 and 2 units of raw 4. Okay, so the next thing I need to go back and change my constraint. So I go back and change my constraint logic. And so this one row right here for my constraints, I'm going to set the reference to BOMs. So now we have a reference, a reference for bill of material, and then go click the ellipsis, and then go in and access the references. So instead of consuming by bill of materials, now we're just going to consume by material. But what we're going to consume is the BOMS M name, and the quantity is BOMS QTY. Oops, do I have this something wrong here? Let's do this. BO component material. There we go. I used M name, and what I really want is the component material, not the name. That's the link material, the finished good. I want to have the component material. So we did, again, we went back and we set the reference for my constraints on my bill of material, and then have those specified using the bill of materials, a component material. One key thing here is we're not using a consumption type of bill of materials here, because the bill of material is implicitly defined in the table rather than explicitly defined with the material. So now we need to go back and do the exact same thing with that. We've done it for the constraint logic. We need to do the exact same thing for our consumption. So I'm going to go back to my task sequence. And if I open my task sequence here, there's my task sequence. I need to do one thing first, let me not forget, is expand my processing task and put the material reference table. Just make this a little bigger so you can see what I'm doing here. So this is the materials reference table name, so I have to give it the link here. And once I do that, I'm able to access that in the individual tasks. So now I have the bill of materials. My consumption is no longer a bill of materials. And I'm going to do the same thing that I did before. In the constraint is I'm going to have BOMS component material, and then my required quantity, BOMS QTY. So we did that for server 1. We need to do the same thing for server 2 and server 3. So let me go to server 2 and open that up. And definitely one argument for using custom objects, because I could just update the properties, but we didn't do that from the beginning, so I will just go and adjust these all manually. So we want to do material, and then component material, and then corresponding quantity. For server 2, last thing for server 3, expand processing tasks, material name, BOMS, and then go back in. The consumption here, 10, it's going to be a material, and we're going to use component material, and then the required quantity, QTY. Okay, so let me just check all of these things. So I set the consumption type to be material. I specified the table there, and then I specified the table here. Did the same thing for server 2, same thing for server 1. And so now I don't have the bill of material explicitly defined within the material elements. And so when I run, though, we can see that we're still consuming those same materials. So I'm consuming 2 of raw 2 and 1 of raw 1 for each one of A, and 1 of raw 3 and 2 of raw 4 for each one of B. So I'm achieved the exact same thing. It's just I have the bill of materials specified in that table structure. So if we let this run, again, we should see the exact same behavior because I defined infinite availability for the 2 Part A bills of materials. So the Part A's are going to continue to be processed. Part B's are going to be blocked, exactly like we saw before. So what's the advantage of this method of moving the bill of materials into the table structure? Well, imagine doing a model where you have hundreds of materials and more complex bill of material structure where you need multiple materials in different quantities and so on. Then we can use the table structure to import all of that information from your planning system, right? So if you have that information in a database or you can export it to a CSV file, we can import that information into the table directly. Also, we could go to our parts table and use the auto create, right? So there's still the auto create option. And so we could also incorporate the material elements all from data. In this particular model, I only have part A and part B here, and that's because I'm using this table to generate the observations. But if I'm not generating observations from this table using the random row, I could also put all of the materials here. I could put the raw materials in this table, and then I could auto create all of the materials. And then by linking the bill of materials, I could also incorporate multi-level bills of material where, a particular subassembly, for example, is comprised of raw materials, and then a subassembly is assembled into higher level products. So by incorporating the table structure, it simplifies significantly adding all of that logic. Otherwise, I'd have to go into each one of the material elements and define its bill of materials and so on. So the table structure just makes it easier to deal with the data. And so we'll see that incorporating that logic in the next couple of video modules. For this one, I'm going to end it here with just the idea of how to put it in the table. And then in subsequent video modules, we will use that auto create logic that I mentioned before. And we'll also see the incorporation of multi-level bills of material using this same table structure.